Hello everyone. Let's start with a thought experiment. Imagine you're in a hot air balloon rising higher and higher into the sky. You look down and wonder, is Earth's pull on me still the same? At a height h above Earth's surface, the distance from Earth's center becomes r plus h. The gravitational force now is F equals g multiplied by me multiplied by m divided by open bracket r plus h close bracket squared. So the acceleration due to gravity at this height is g of h equals gme divided by open bracket r plus h close bracket squared. Since the denominator gets larger, g of h is smaller than the surface value of g. In other words, the higher you go, the weaker Earth's grip, like slowly loosening a rope as you climbed upward. Now let's zoom in. What if the height h is tiny compared to Earth's radius, say on top of a mountain or inside a tall skyscraper? In this case, we can simplify using the binomial expansion. The formula becomes g of h is approximately g multiplied by 1 minus 2h divided by re. This means for small heights, gravity decreases almost linearly with altitude. So yes, technically, you weigh a little less on Mount Everest than at sea level. Sadly, the difference isn't big enough to skip gym day, but it's real and measurable. Alright, now let's head underground, maybe inside a deep mine shaft. Does gravity get stronger or weaker as we go down? According to the shell theorem, only the inner sphere of radius a minus d contributes to the force. The outer layers cancel out perfectly. So the effective acceleration becomes g of d equals g multiplied by 1 minus d divided by re. That means gravity decreases linearly with depth. Go deeper and the pull softens. At Earth's center, g becomes 0. You would literally feel weightless. Imagine floating at Earth's core, pulled equally in all directions, with no net force. Let's now put the two cases side by side. Above the surface, g decreases with the inverse square of distance, 1 over r plus h whole squared. That's a curved drop. For very small h, it looks almost linear with slope minus 2g divided by r. Below the surface, g decreases exactly linearly with slope minus g divided by r. So, the story is, gravity is maximum at Earth's surface and it decreases whether you climb up into the sky or dig down into the earth. It's like Earth saying, I pull you the hardest at my skin, but if you move away in either direction, my grip loosens. Why does all this matter? Because we see it in everyday life and technology. At higher altitudes, gravity is weaker. This is why satellites orbit Earth at lower g and astronauts feel weightless. At great depths, miners experience slightly reduced weight, not enough to notice casually, but significant for geophysics. Scientists also use these variations to study Earth's density profile and even detect underground mineral deposits. So, the change in g isn't just theory, it has practical uses, from space missions to mining industries. Let's make this real with a calculation. Suppose Earth's radius is 6.37 times 10 to the power 6 meters and surface g equals 9.8 meters per second squared. Case 1, altitude. At h equals 1000 kilometers, g of h equals g multiplied by r divided by r plus h squared. Substitute values and you get about 7.3 meters per second squared. Case 2, depth. At d equals 1000 kilometers, g of d equals g multiplied by 1 minus d over r. Substituting values gives about 8.25 meters per second squared. So what's the insight? Going up by 1000 kilometers reduces g more dramatically than going down the same distance. That's why satellites quickly feel weaker gravity, while miners underground still feel most of Earth's pull. Alright, Let's tie everything together. At a height h, g of h equals g multiplied by r over r plus h whole squared. For small heights, it decreases almost linearly. At a depth d, g of d equals g multiplied by 1 minus d over r, dropping steadily until it vanishes at the center. So gravity is strongest at Earth's surface and becomes weaker whether you rise above or go below. This concept explains satellite orbits, astronaut experiences, and even why geologists can study Earth's interior. So next time you hike up a mountain or read about a mine shaft, remember, gravity itself is changing with you. That's the beauty of physics. It reveals hidden patterns in the forces we take for granted every day. See you in the next session with another exciting journey into the universe of physics.